Today, we will be discussing the effect of temperature on radical polymerization and introducing a concept known as sealing temperature. Before we get ahead of ourselves, let us do a quick overview of radical polymerization. Radical polymerization can be broken down into three major processes: initiation, propagation, and termination. The first step in initiation is the formation of a radical. This step consists of an initiator, such as peroxides, acyl compounds, etc., which are broken down to form radicals. This can be done with the application of heat to induce thermolysis. For simplicity, we have a hydrogen peroxide molecule here. The image on top is a simplified model. These pink circles are oxygen atoms. Each oxygen atom is attached to or holding hands with another oxygen atom and a hydrogen atom. You can think of these green circles as electrons, since each bond consists of two electrons. However, in reality, electrons are clouds and the molecule will not look like this. The image below is another representation of the initiator. The colors of the atoms between the two images correspond. So what happens when we break this attachment or bond between the two oxygen atoms? So here we can see the bond between the oxygen atoms has been broken. Now we have formed two radicals from the single hydrogen peroxide molecule. The oxygen atoms are frowning or unhappy because they have an unpaired valence electron, which is what a radical is. Since molecules with unpaired valence electrons are energetically unfavorable, radicals are highly reactive compounds. Radicals want to react with and form a bond to other molecules to no longer exist in this highly energetic state with the unpaired valence electron. The next step in the process is the formation of an active center by the transfer of the unpaired valence electron to a monomer. Here we have a radical on the left and an ethylene monomer on the right. And ethylene is the monomer component of polyethylene. The pi bond of the ethylene monomer will be attacked by the radical. Again, these are simplistic models that do not accurately represent the shape of the molecular orbitals. In reality, the pi bond involves the sideways overlap of the two lobes of the two p orbitals. Nevertheless, for simplicity, we can understand this process as the formation of a bond between the initiator and the monomer, as well as the transfer of the unpaired valence electron to the terminal carbon atom of the chain. The carbon atom with the unpaired valence electron is referred to as the active center. This is because monomers will be sequentially added to the active center, which lengthens the polymer chain. The active center will always be at the end of the propagating chain. The next step in the process is propagation. Here we have a growing chain with an active center at the end. The ellipses means that the chain continues beyond the boundaries of this image. Somewhere along at the beginning of our chain will be our initiator, as we discussed prior. So propagation occurs when the carbon at the active center forms a bond with an incoming monomer. The unpaired valence electron is once again transferred to the terminal carbon of the chain. Hence, the chain grows by another monomer unit, and the active center always remains at the end of the chain, allowing the chain to continue propagating by reacting with more monomers. In the final step of radical polymerization, we have termination. Here we have shown termination by a process known as combination. In combination, two active centers from two different propagating chains will combine to form one long polymer molecule. We can see here that one chain with n propagating units combines with a propagating chain with m units to form one long chain with m plus n units. In this case, a polyethylene polymer is formed. Another kind of termination process is disproportionation. Unlike termination, disproportionation involves the transfer of a proton from the penultimate carbon on one chain to the other chain, such that the two propagating chains form two separate polymer molecules. So why do we even care about radical polymerization? Radical polymerization creates many of the important polymer materials that we use in our daily lives. For example, polyethylene is used in bottles, bags, packaging. Polyvinyl chloride is used for pipes, insulation, window frames, etc. You also probably know polystyrene from polystyrene foam that makes up disposable cups and plates. So all of these are very important polymers, and they are produced by radical polymerization. So what role does temperature play in all of this? To discuss the effects of temperature on radical polymerization, we will derive something called the sealing temperature. Let this square be a monomer unit. As discussed earlier, propagation involves the addition of a monomer to the end of a growing chain. This results in a chain that was once originally n units long, becoming a chain that is n plus 1 units long. I want you to take notice that this propagation reaction is reversible. This is important. We will now introduce the effect of temperature through the application of Gibbs free energy. Gibbs free energy is related through Legendre transforms to enthalpy and internal energy. Essentially, it is a thermodynamic potential that we can use to characterize the spontaneity or energetic favorability of a process. Assuming a constant temperature and pressure, a process will be spontaneous if there is a reduction in Gibbs free energy. In other words, the propagation reaction will be energetically favorable if the associated change in the Gibbs free energy is negative. The change in the Gibbs free energy for the propagation reaction is the standard state Gibbs free energy and a term that characterizes the activities of the reactants and products. Kp is the equilibrium constant for the propagation reaction. R is the gas constant, and T is temperature in Kelvin. Let us assume that the reaction has reached equilibrium. For this to happen, the change in the Gibbs free energy must be equal to 0. If there is a change in Gibbs free energy, then the relative proportions of products to reactants is changing, and hence our system is not equilibrated. If we set delta G, P, equal to 0, we can determine the standard state delta GP as equal to this equation here. Let us revisit our propagation reaction. We have a chain that is n units long that grows by 1 monomer unit to become n plus 1 units long. If we consider our system as a whole, there are many chains of many different lengths that are undergoing propagation. Hence, if we sum over all of these lengths, we can obtain a total concentration for all propagating radicals. The equilibrium constant for a reaction is the concentration of the products over the reactants. For the propagation reaction of all the radical chains, the equilibrium constant is the concentration of all the radical chains that have been grown by 1 monomer unit divided by the concentration of the initial length of the radical chains, as well as the concentration of the monomer. So polymers are typically composed of very long chains. So if we take into account the length of an entire chain, the addition of a single monomer unit is going to have minimal effect on the overall length of the chain. So the concentration of the radicals of a specified length is going to be similar to the concentration of those same radicals plus the length of one more monomer unit, as we have specified here. So to better understand this rough equality, we can imagine a distribution of the polymers. So we can take the weight fraction or number fraction of the polymers versus their degree of polymerization or the length of a chain. So if we have two chains that differ in length by only 1 monomer unit, we can see that as a pretty small increment or difference in chain lengths between the two chains if we're considering long polymer chains. And therefore, there's going to be a minimal difference in the concentration of those two different chain lengths. So if we have this rough inequality, we can plug that into our Kp equation, and we can get that our equilibrium constant for propagation is 1 over the equilibrium concentration of monomer. Returning to the standard state Gibbs free energy change for the propagation reaction, we can note that we can write this value in terms of the standard state change in enthalpy and the change in entropy. We note here that polymerization is generally an exothermic process. Hence, our delta HP is going to be negative. Polymerization also results in greater ordering, and hence we can expect delta SP to be negative, which would make this term as a whole positive. So the higher the temperature, the larger this positive term, and the more positive the change in Gibbs free energy, which is unfavorable. Therefore, we can expect that there is a ceiling temperature at which the reaction is no longer energetically favorable, or our delta GP becomes positive. If we equate this equation to what we had prior, we get the following equation. If we also plug in for Kp what we derived prior, we can get this equation. If we solve this equation for temperature, which we have done here, we can get an expression for temperature in terms of the standard state enthalpy, the standard state entropy, and the concentration of monomer at equilibrium. We will define our sealing temperature, or Tc, as the point at which the equilibrium concentration of monomer is equal to the bulk concentration of monomer. This is because at this point, there is no longer any driving force for polymerization. Ultimately, we would get the following formulation for our sealing temperature. So it's great that we have this formula for sealing temperature and all, but to better picture what this means, we can imagine these following scenarios. Let us assume our reaction is proceeding at a temperature less than the sealing temperature. We're also going to assume that the temperature is sufficiently high enough that the monomers are able to diffuse sufficiently fast enough to the active centers and react. In this case, the equilibrium concentration of monomers is less than what is present currently in the bulk. Hence, the reaction will shift in favor of polymerization to move towards equilibrium and decrease the amount of monomer present. If we increase the temperature to be at the sealing temperature, at this point, the concentration of monomer at equilibrium is equal to the concentration of monomer in the bulk, and there is no driving force for polymerization or depolymerization. Hence, we can see that these two arrows for the forward and backward reaction are equal. As we increase the temperature beyond the sealing temperature, the amount of monomer at equilibrium becomes greater than the current bulk concentration. As such, to move towards equilibrium, the reaction shifts in favor of depolymerization to increase the amount of monomer present. The concept of sealing temperature is important as it presents an upper limit to the acceleration of polymerization by an increase in temperature. Generally, we think that heating up a process will accelerate the reaction. This is because the rate constant for most reactions generally has an Arrhenius relationship with temperature. However, at a certain point, we hit a ceiling where polymerization is no longer energetically favorable. Increase in temperature beyond this point will result in undesirable effects such as depolymerization. Let us take a look at some example values of sealing temperatures. Here, we can see that styrene has a sealing temperature of 400 degrees Celsius, while alpha methylstyrene has a sealing temperature of 61 degrees Celsius. This is important as it demonstrates how monomer structure can affect the temperature at which polymerization can occur. Compared to styrene, alpha methylstyrene has an additional bulky methyl side group that introduces steric hindrances to polymerization. Hence, the sealing temperature for alpha methylstyrene is lower when compared to styrene. From this, we can see how sealing temperature is important in determining the temperature at which we can conduct the polymerization of a certain monomer. In this case, we have to conduct the polymerization of alpha methylstyrene at a lower temperature than we can for styrene. I hope you learned a little bit more about radical polymerization and the effect of sealing temperature. Thank you for watching.